Hello, and welcome back to the course on thermodynamics. So this is still unit 4, the last unit for this course. So far we have discussed about heat engines and internal combustion engines. So the work done by heat engines is just the heat input plus the heat output, so QH plus QC. And the efficiency is just the work output over the heat input. So in this lesson, we will be talking about refrigerators. So basically, a refrigerator is the reverse of a heat engine. So the same principle also applies for both refrigerators and air conditioners. So a refrigerator again is just a heat engine operating in reverse. Now, if you recall the diagram for a heat engine absorbs heat from a higher temperature region and does work and then releases some of the heat, exhausts some of the heat to a lower temperature region. But as you can see in this diagram, the refrigerator absorbs heat from the lower temperature region, the inside of the refrigerator, and it can only do that if work is being done on the refrigerator, if heat is being pumped from the cold region to the hot region. So heat is being absorbed by the refrigerator from a cold region, and it does that by doing work on the refrigerator, and then it releases heat to a hot or higher temperature region. Take note that heat naturally flows from higher to lower temperature region, from a hot body to a cold body. So it is not natural for heat to naturally flow from from a low temperature body to a higher temperature body. That is why you need to do work if you want to make heat flow in the reverse direction. So basically, a refrigerator is a device that makes heat flow from a colder region to a hotter region by doing work on it. So work done on the refrigerator is basically just the same. The heat released to the hot temperature region, QH, plus the heat absorbed from the cold region or the lower temperature region. But in this case, unlike in the heat engine, where QH is positive and work is positive and QC is negative, here it's the reverse. So since heat is now being released to the hotter region, QH is negative. And QC is positive because this is heat absorbed. And work is negative because work is now done on the refrigerator by an external device. And it's actually done by a pump. So work is negative. This is now work done on the refrigerator. Take note, the refrigerator does not do work. Actually, work is done on the refrigerator. So the coefficient of performance in this case is basically just the thermal efficiency of your refrigerator. And it's described by the coefficient designated as K. And it's basically just the heat absorbed by the refrigerator over the work done on the refrigerator. So in this case, in order to get a positive value, since work is negative and QC is negative, there's a negative sign here. But you can also use the absolute values, and if this is easier for you. Okay. So this is now for a refrigerator, the working substance is what we call a refrigerant, and in most refrigerators, it's usually freon. So a freon is usually a gas. It can actually convert its phase from gas to liquid during the cycle. So these are the parts of your refrigerator. So your refrigerator has two types of coils. The evaporator coils, these are actually found inside the refrigerator, and the condenser coils, which are usually found outside of the refrigerator. So the working substance, the refrigerant, actually travels through these coils. So they travel through the expansion valve, through the evaporator coils, to the compressor, to the condenser coils, and back. So it's a cycle. So the expansion valve expands the refrigerant liquid. So when it expands, it actually decreases the temperature and the pressure. So you will have a low pressure and low temperature or cold refrigerant, and it's still in liquid form. So that's the purpose of the expansion valve, to decrease the temperature and pressure, so to make it a low pressure cold liquid. Now, so since you now have a very cold liquid in this evaporator coils, and this is placed inside the refrigerator, if you place food inside the refrigerator, and obviously it will have a higher temperature as compared to the evaporator coil, so naturally heat will flow from your food, which has a higher temperature, towards the evaporator coils. So that's actually how any object placed inside the refrigerator is being cooled, by actually absorbing the heat from those things, from those objects, from those food, absorbing the heat, and that's absorbed by the evaporator coils, by the low pressure cold liquid in the evaporator coils. So when the low pressure cold liquid absorb this heat from the food that you place inside the refrigerator, they will actually evaporate. That's the reason why they're called evaporator coils, because the low pressure cold liquid absorbs heat and it will evaporate, and the refrigerant now becomes a gas. From originally a freon liquid, it now becomes a freon gas. It's now a low pressure but a warm gas, higher temperature gas. It already absorbs heat. So this liquid, the refrigerant, then goes to a compressor. So the compressor compresses the refrigerant gas, and when you compress the gas, you actually increase its temperature and pressure. So you now have a high pressure hot gas flowing through the condenser coils. And now, since the condenser coils are outside of the refrigerator, so it's hotter as compared to the outside environment, then naturally the heat from the uh, condenser coils will be released to the outside environment. And the gas will now condense, the high pressure hot gas will now condense into high pressure regular temperature liquid, and this liquid will go back to the expansion valve again, and the process will repeat. It will absorb heat from the food or any object that you place inside the refrigerator, and then it will release that heat outside of the refrigerator via the condenser coils. So that's how a refrigerator works. The evaporator coils absorbs heat from the food that you place inside the refrigerator, and that heat is released by the condenser coils outside of the refrigerator. So this is a typical refrigerator. The evaporator coils are usually inside the refrigerator, the blue ones, and the orange one, the orange coils, are the condenser coils. They're actually usually outside of the refrigerator. So usually these lines that you see here inside your freezer, those are the evaporator coils. And if you buy a new refrigerator, you must always read the manual of the refrigerator. And especially, you must not use pointed objects when defrosting, when clearing the frost in your freezer, because you might damage the evaporator coils. If you damage the evaporator coils, meaning say there will be a hole there or a leak there, then your refrigerant, your freon gas, your refrigerant liquid or gas will now leak from your coils, and there's no more working substance working in your coils, then your refrigerator will not work, if that is the case. So you need to patch that say hole, and supply a new batch of refrigerant or freon gas or liquid into your refrigerator system. So be careful of the evaporator coils. So this is an example of an exposed condenser coils. This is usually from this picture is actually the back of a water dispenser. And in modern refrigerators, they now usually cover the condenser coils, so that you will not be exposed to the high, you cannot accidentally touch the high temperature of the condenser coil. So usually they cover it with a metal casing. But again, that's how a refrigerator works. It absorbs, if you put up food here in your freezer, then the heat from the food will be absorbed by the evaporator coils, and that will be released by the condenser coils, making your food colder or have a lower temperature or freezing your food. Okay, an air conditioner obeys the same principle as a refrigerator. So it has an evaporator coils, and the evaporator coil is usually in the inside part of the room, and the condenser coils in the outside part of the room. So warm air is being absorbed by the evaporator coils, and this warm air is released outside. So heat is absorbed by the evaporator coil, the heat in the room from the objects in the room, say from your body, you're releasing heat. So that is absorbed by the evaporator coils, and that is released by the condenser coils. So the same principle actually for air conditioners and refrigerators. A variation of the air conditioner is a heat pump. So a heat pump or a heater. And we can't relate to this because we don't have a winter condition in our country, in the Philippines. But in countries where there are winter season, very cold seasons, they have a variation of the air conditioner wherein inside the room are the condenser coils and outside the room are the evaporator coils. So basically you reverse your air conditioner so that hot air will now blow inside the room, because during winter seasons the outside air is very cold or have a very lower temperature. So you absorb in a heat pump, it absorbs heat from outside of the house and it releases that heat inside the house to warm your house during winter seasons. So in a heat pump, the evaporator coils are outside while the condenser coils are inside the room. Okay. Another term for the coefficient of performance of a refrigerator or air conditioner is what we call the energy efficiency rating. So basically, it is just the coefficient of performance of an air conditioner or refrigerator in terms of the units of heat, current, and power. So the heat absorbed by your refrigerator is basically just the heat current times the time. And the work done on the refrigerator is basically just the power times the time. So you can cancel T. So basically, you can calculate the coefficient of performance of your refrigerator if you know the heat current and the power rating of your refrigerator. And that is basically your EER, energy efficiency rating, only if the unit of your heat current is in British thermal units per hour and the unit for the power is in watts. So if the unit of H is in BTU per hour, British thermal units per hour, and if the unit of P is in watts, then the ratio of these two numbers will give you the EER. So one British thermal unit is just 1055 joules. 1055 joules. So another term related directly to the energy efficiency rating is the energy efficiency factor. And this is usually what we see when we buy refrigerators or air conditioners. So when you buy refrigerators or air conditioners, you will see this yellow tag where you have an energy guide term here, and there the number stated here is what we call the energy efficiency factor. So it's just directly related to the energy efficiency rating. So higher EEF, higher energy efficiency factor, means lower operating cost because your refrigerator becomes more efficient. So lower operating cost. So lower power consumption and basically lower electricity bills. So the higher the energy efficiency factor, the lower will be the energy consumption of your refrigerator or air conditioner. Okay, let's now have an example of a refrigerator. So let's analyze a freezer. So a freezer has a coefficient of performance of 2.40. It converts 1.80 kilograms of water at 25 degrees Celsius to 1.80 kilograms of ice at negative 5 degrees Celsius in an hour. So if you place 1.80 kilograms of water inside this freezer, it will convert this into ice at negative 5 degrees Celsius in just an hour. So the first question is, what amount of heat must be removed from water at 25 degrees Celsius to convert it to ice at negative 5 degrees Celsius? So this problem is actually just a problem in calorimetry in unit number 1. So basically you have water at 25 degrees Celsius, and then it will become water at 0 degrees Celsius, and then it will undergo a phase change. So from liquid water at 0 degrees Celsius, it will become solid ice at 0 degrees Celsius. Take note, phase change. There's no temperature change in a phase change. And then, when it is now an ice, solid ice at 0 degrees Celsius, it will further release heat to become ice at negative 5 degrees Celsius. So that one. So basically, you have a phase change first from water at 25 degrees Celsius to water at 0 degrees Celsius. Then, a temperature change. A phase change, then another temperature change. So you have 3 steps actually here. So the total heat will be the temperature change of the water from 25 to 0 degrees, the phase change of water from liquid water to ice, and then the temperature change of ice from 0 degrees Celsius to negative 5 degrees Celsius. So you have 3 terms here. So substitute the values. So you have 1.80 kilogram for the mass. This is the specific heat of water. Final temperature of water is 0 degrees Celsius. Initial is 25 degrees Celsius. And this is just the latent heat of fusion for ice to water and water to ice transformations. In this case, it's negative because it releases heat. And then you have the C of ice, specific heat of ice. Again, specific heat of ice and water are not the same. Actually, the specific heat of ice is just 1/2 of that of water. So the final temperature is negative 5 degrees Celsius minus the initial temperature is 0 degrees Celsius. And you will have an answer of negative 808,650 joules, or negative 808 kilojoules. So this is the amount of heat released by your water to become ice at negative 5 degrees Celsius. Now, the second question is, how much electrical energy is consumed by the freezer during this hour? So how much energy does it consume by freezing this water into ice at negative 5 degrees Celsius? So we know that the coefficient of performance is just the heat absorbed by the refrigerator over the work input or the work done on the refrigerator. So the heat absorbed by the refrigerator is just equivalent, basically, the negative of the heat released by the water. So take note that the water releases heat, and this heat is absorbed by the refrigerator. So meaning QC is equal to negative Q, the negative of the released heat. So the positive version of the heat released by the water. So the heat released by the ice or the water is absorbed by the refrigerator. So we now know QC. We are given with the coefficient of performance, so we can now solve for the work done on the refrigerator. So it's QC over K. And you will get a value of 336,937 joules. But this is actually not what is asked in the second problem in letter B. We're actually, this is actually what is asked. The electrical energy consumed by the freezer. So the electrical energy consumed by the freezer is basically the work done on the freezer. So the work done on the freezer in order to convert water into ice in just 1 hour. So this is now the amount of energy supplied to the refrigerator in an hour. So this is the work done on the refrigerator in an hour. So how much heat, the last question is how much heat is wasted or is delivered to the room in which the freezer sits. So this is now the heat exhausted by the condenser coils. So we're actually solving for QH, and this is just the work minus the QC. So take note, this is the absolute value of the work, but in actuality, in our equations, the work is actually negative. So it's a negative of this. This is just the absolute value, the amount of energy supplied to the refrigerator. And the work is actually the negative of this, negative 300, because this is work done on the refrigerator. And QC is positive. So basically you have negative 336 minus QC, which is positive 808, and you will get a negative answer because QH is negative. QH is the heat released by the refrigerator to the outside of the refrigerator, the higher temperature region. And you will get a value of negative 1.145 megajoules. So that one. So let's have another example. So this is now an air conditioner. So a window air conditioner absorbs 9.80 times 10 to the 4 joules of heat per minute from the room being cooled, and in the same time deposits 1.44 times 10 to the 5 joules of heat into the outside air. So it absorbs this amount of heat from the room, and it releases this amount of heat into the outside of the air conditioner, outside the room. So the question is, what is the power consumption of the air conditioner in watts? Okay, if you want to solve for the power is work per unit time. So you need to solve for the work done by, or work done on your refrigerator. So to solve for the work done, it's just QH plus QC. So our QH is this one, our QC is this one. But take note, usually in word problems, you can't see the negative signs, but you just see the words. Deposits heat into the outside air. So meaning this is negative actually, negative 1.44 times 10 to the 5. And this is absorbed, so this is positive 9.80. So you need to incorporate the negative signs when you are calculating the values here. So it's negative, it should be negative 1.44 because that is QH, it's negative, it's being released. And this is positive 9.80 because this is being absorbed. So you now can solve for the work done. And the work done is in work done on the refrigerator is expected to be negative because this is work done on the refrigerator, not by the refrigerator. It's on the refrigerator. So it should be negative. So when you're dealing with air conditioners and refrigerators, the work that you must obtain must always be negative. If it's positive, then your solution is wrong. So the power is just work per unit time. In this case, we'll just use the absolute value of the work because this is basically just the energy consumed per unit time. So the energy consumed is basically positive 4.60, the absolute value of negative 4.60. So positive 4.60 times 10 to the 4 joules per minute. So 1 minute, the time is 60 seconds or 1 minute. And joules per second is the unit called watts. So 767 watts. So this is approximately 1 HP, 1 horsepower air conditioner. So 1 HP is around 746 watts. Okay, so that is the power consumption of this air conditioner in watts. So it supplies 767 watts of power to your refrigerator. So what is the energy efficiency rating of the unit? So if you want to solve for the EER, you must solve for the heat current and the power. Since we already know for the power in watts, we need to solve for the heat current in British thermal units, BTU per hour units. British thermal units per hour, na unit. So the heat current is just the change in heat over change in time. So heat absorbed over time. So we know QC, we know time is 1 minute. We need to convert the joules into British thermal units using this conversion factor, and we need to convert the minute into hours using this conversion factor. So you cancel minute here, you cancel the joules, and your final unit will be British thermal units per hour, BTU per hour. So you will get a value of 5,573 BTU per hour. So if you now have the heat current in BTU per hour and the power in watts, you can just divide the two numerical values to obtain the EER, which is 7.3. So the EER actually is related to the coefficient of performance. So if you calculate the coefficients of performance in this case, you have absolute value of QC, which is this one, over the absolute value of work, which is this one, you will get 2.13. And 2.13 or 7.3, the EER is actually 3.4 times the coefficient of performance, which is 2.13. So in the future, if you want to solve for the EER and you're already given the coefficient of performance K, then you can just approximate it to 3.4 times the coefficient of performance K. So that's it for this lesson. So we have now discussed two types of device, which is the heat engine and the refrigerator. So before we can fully discuss the heart of this unit, which is the second law of thermodynamics, we still need to discuss one last concept. And that concept is entropy. So we'll discuss that concept in the next lesson. So I will see you again in the next video lesson.